Okay, so these are the solutions for coursework exam number 2. Okay, so the first question here asks us, it said, suppose that n is an integer such that n mod 15 is equal to 7. Determine what is 4n squared plus 3n mod 15. So the mod is the same as this. So we have to use this somehow to figure out what this thing is, mod 15, and it gives us a little bit of an explanation here. In other words, if division of n by 15 etc gives a remainder of 7, then what is the remainder? So they are giving you a little bit of a guide here. So let me pull up the canvas here. Okay, so what does it mean here in plain words? Okay, so let's just write down what we are given. So this is question 1 part A. So we have here that n mod 15 is equal to 7. Okay, what does this mean here? It means that when n here is divided by 15, the remainder is 7, not 17, right? Okay. Right, the remainder is 7. So we need to translate this now into a form which we could use. Okay, so any number with a remainder of 7 when divided by 15 has to look like something. So that's something that I wanted to look like is this. So I wanted to look like n is equal to 15k plus 7 was for some integer a, right? So now I'm seeing that I can approach this question in 2 ways. Either I can use this definition here which I just formed, or I could somehow use the definition of congruences with the fact that the remainder is 7 and then solve it, right? But since we only care about the remainders mod 15, since we only care about this remainder, then I can replace n in the question that they ask us, which is 4n squared plus 3n, with anything that has the same remainder. So we have this here, right? The remainder is this thing here, 7. So I can replace n in 4n squared plus 3n with 7. Because why? Congruences are preserved under addition and multiplication. So I can replace, so in 4n squared plus 3n, right, this will be congruent to 4 into 7 squared plus 3 into 7 mod 15. Okay, if we work out this part here, this will be, so this part here will be 4 by 49 plus 7 3 is 21. So I get 196 plus 7 3 is 21, which is 217. Okay, now I have to reduce 217. Okay, because it says that it has a remainder of 7. So I can take, okay, so I can take 217 and divide it by 15, since it's mod 15, I will get how much is this? 14 multiplied by 15, and the remainder, if you want to put r, is 7. Okay, so therefore 217 is congruent to 7, because 7 is the remainder, mod 15. So n here, what I wanted was, or is, 7. Now it just so happened that the question here had us replace n in this here, in this form of the definition with 7, and the remainder happen to be 7 as well, right? This is just coincidence, right? It doesn't always happen like this. It doesn't always happen like this. So this is just coincidence. Now, what about using this definition here, this one here? Okay, I'm saying that n is equal to 15k plus 7. So how can I use this definition here? Now, because the problem asks us for the remainder, they ask us for the remainder when 15 here, when divided by 15, then I can replace this n here in 4n squared plus 3n with 15k plus 7. This means that any term that has a factor of 15 will disappear when we take the remainder mod 15. So if I directly substitute n to be 15k plus 7, I should get the same answer. So in fact, I have to get the same answer. So let's work it out like this now. So if you want to write, so this is like method 2. So n is equal to 15k plus 7. Okay, and k was an integer. Then we want, just for proper steps, we want 4n squared plus 3n mod 15. So therefore, 4n squared plus 3n will be equal to 4 into 15k plus 7 squared plus 3 to 15k plus 7. So this will be equal to 4 into 15k plus 7 by itself. That will give me 15 by 15, which is 225k squared, plus 15 multiplied by 7 plus 15 multiplied by 7, that's 210k, plus 7 sevens, that's 49. Plus, let's just expand this out one time. 15 by 3, that's 45, and 7 by 3, that's 21. Okay, plus 21. So this will be equal to 225 by 4k squared, that's 900k squared. 210 by 4, that's 840 plus is 45, that's 885k, and 49 multiplied by 4 plus 21, that's 217 again. Okay, that's good, right? So look, I'm seeing the same 217 here, but I have two terms here in front. So we want mod 15. So it means here now that anything or any term here with 15 as a factor is what? 0 mod 15. In other words, when we divide by 15, I have to get no remainder, right? So this 900 has to be 0 mod 15, and this 885 also has to be 0 mod 15. Okay, so let's actually write that out. We want mod 15. Okay, so any term, I guess you could write that here, any term with 15 as a factor is 0 mod 15. So that is my justification. So I have 900 k squared will be congruent to 0 mod 15. Why? Let's put a little bracket here. So since 900 is equal to 15 by 60, and as well for the 885 k, this is congruent as well to 0 mod 15. Why? Because since 885 is equal to, how much is this? 59. Okay, so both of these here both of these here have a remainder of 0. So just this one, but we already did that from before in the first method, right? So we just reduce 217 to mod 15. So that will give me 217 divided by 15 like before, which is 15 by 14, which was 210 with a remainder of 7. So therefore, once again, the 217 is congruent to 7 mod 15. Okay, so n will be equal to 7, just like before. Okay, so any method that you choose will give you the same answer. All right, moving on to part B now. Part B asks us to, it said if k is any even integer and m is any odd integer, prove that this expression here is divisible by 4. So it is divisible by 4. Okay, so that is what we have to show. So this is part B. So we could start by saying let k be any even integer and m be an odd integer. Okay, then what is the form of an even integer and an odd integer? One, for the even we have 2k, and for the odd we have 2k plus 1, right? But in the question we already have k, so we're going to just have to use different variables. Okay, I could say then there exists, let's say, some integers a and b, okay, such that k is equal to 2a, so this is the even one here, and for the odd one I'll say m is equal to 2b plus 1. Now I'm going to substitute this k and this m into our expression, break it down as much as possible, and then show that that is divisible by 4. So I'm supposed to get some integer multiplied by 4. Okay, so let's substitute this now. So the first one will be, so let's do it piece by piece actually. So for the first term, right, for the first term I'll have k plus 2m, which is equal to 2a plus 2 into m, which is 2b plus 1. So this will be equal to 2a plus 4b plus 2. And then I can factorize out the number 2 from all of this. So I'll have 2 into a plus 2b plus 1. Okay, so this is the first part here. Then for the second part, so I know that the expression is k plus 2m all squared, right? But I need to work out what is k plus 2m by itself first, right? And then square that, right? And for the second term, so I'm just doing it in parts here, so it's easier to see, so we don't get confused. So the next term, so the second term is k minus m plus 1. So I'll have 2a minus m, which is 2b plus 1, and then the extra plus 1 here, right? So plus 1. So then I'll have 2a minus 2b, so the negative sign will come on the inside, negative minus 1 plus 1. So this will be 0 here, and then the 2a minus 2b, well, both of them have the integer 2, so I'll just factorize out 2 into a minus b. So now I have the two terms, right? So I'm going to substitute it back into the expression in the question. Let's just pull back up the question, which is k plus 2m all squared minus k minus m plus 1. Okay, now we're going to substitute everything back into the original question. So I'll have k plus 2m all squared. In fact, since I'm squaring, right, maybe it might be beneficial because you can be quite long to square this immediately here, meaning that let's put some side working. So from the side, I know I have to get k plus 2m all squared, which is equal to 2 into a plus 2b plus 1 all squared. So that will be 2 squared, which is 4, and then a plus 2b plus 1 all squared. And then I take this now, right, and I put it into this my expression. So let's do the same for this one. So this one will be what was it again? K minus m plus 1. So I'll have k minus m plus 1 all squared is equal to 2 into a minus b all squared, which is equal to 4 into a minus b all squared. We'll handle this after. Let's just substitute everything now. Right, minus k minus m plus 1 all squared. So this will be equal to 4 into a plus 2b plus 1 all squared, because that's this part here. Then we have minus, so I'll have minus 4 into a minus b all squared. I did that because I recognize here that I have a number 4 and a number 4, and both of these terms here are squared. So I can factorize out the number 4, and I did that specifically because the question asked to show that it is divisible by 4. So it's easy to see that I could factorize out the 4 from here and have this a plus 2b plus 1 all squared minus, okay, and I don't need to expand out this nor this, right, because the question asks to show that it is divisible by 4, and I have some integer here a, so I actually have to write a little statement now, or you could write it and you could say that since a is an integer and since b are integers and 2 is an integer and any integer multiplied by an integer will give me an integer, sum of integers are integers, the square of integers are integers, the difference of integers are integers, etc. Then it follows that we could call this part here, we could write out since the expression, right, so after we have written this entire long story about the sum of integers, etc., then we write since the expression is 4 times an integer, then it follows that k plus 2m squared minus k minus m plus 1 all squared is divisible by 4, right? So hence the expression, yes, it is divisible by 4, because that is what we wanted to show. All right, so this was question. In fact, before we move on to question 2, I'm seeing that in the question itself, I mean, if you didn't see, if you forgot to maybe substitute and do that, I'm seeing that I have some sum of integers squared here, and I have this difference and the sum of some integers squared here, and I have a subtraction sign between it. If you remember, if you want to do this another way, I'm thinking, again, like method 2 or something like that, I could recognize here that maybe I can factor the expression using the difference of two squares. Remember that the difference of 2 squared, a squared minus b squared, is equal to a minus b by a plus b. And that looks like my expression here. So in my expression, let's call it something else. Let's call it e, right? Because I already have a and b here. So let's call e k plus 2m all squared minus k minus m plus 1 all squared. If I use the fact that the difference of two squares here, so for me here, a would be equal to k plus 2m and b would be equal to k minus m plus 1. I'm doing this because the question did not say specifically to use the properties of the fact that an integer, an even integer, looks like 2k and an odd looks like 2k plus 1, right? So I'm looking for another way that maybe I could have done this, right? That may be a little bit faster. So I could have recognized this here, and I could have said that a minus b would be equal to k plus 2m minus k minus m plus 1. That would give me k minus k plus 2m. So I could subtract it immediately, actually. So I'll get k minus k, which is 0. Actually, let me write it out. K minus k plus 2m plus m minus 1. Right? So I'll have 3m minus 1. And then for a plus b, I will have k plus 2m plus k minus m subtracted plus 1. That will give me 2k plus m plus 1. Okay, so now I have two expressions for my difference of two squares. Now what I could do is I could say now that e is equal to 3m minus 1 by 2k plus m plus 1. So now this is my e. And then I could inspect my e and I could look at the parity of my new expression here. So in my new expression, I notice that I have, let's look at this one first. I notice that I have 2 multiplied by k. 2 is an integer, k is an integer. So this here is the form of something that is even, right? M was given in the question to be something that is odd, and the number 1 itself is odd. And an even plus an odd number will give me an even number. Similarly here, 3 is an integer, and we have m being odd in the question. So 3 by m, so this part here, this will be something that is odd. And then I subtracting this from something that is odd again. So I have an even plus an odd. So I'll have, sorry, I wrote this 40. Let me rewrite this right. So I have 3, which is an integer, it's odd, multiplied by m, which is odd. So an odd by an odd will give me an odd. And then I'm subtracting this from 1, which is an odd number. So an odd minus an odd, like 3 minus 1, will give me something that is even. So I have even here and I have even here. So if I have 2 even, so 3m minus 1 is represented as something that is even. Similarly for this part here. So now E, so I'm going to call 3m minus 1 something else. So let's get another color. I'm going to call this something like 2 by A and maybe 2 by B, right? And this is multiplied here, right? So it'll be 2 by A multiplied by 2 by B, which is 4 A by B. And this again is of the form 4 by some integer A by some integer B, right? So it looks just like the method that we did before here. Same construction, right? So this here is another way that we could have done this, right? This is another way that we could have done this, but of course using the properties of even and odd integers is much simpler and straightforward. Right, so moving on, so this was the end of question 1. So moving on to question 2 now. We have a statement here and we have to determine a bunch of stuff. Is it true for all integers, none of them, etc., etc.? So let's rewrite the statement. So this is number 2, part A. Okay. So the statement is A cubed plus B cubed plus AB, right? And we have to determine whether this thing is divisible by 4, for some, for none, etc. Now, since A and B are given in the question to be odd integers, right? A and B are odd integers. That means I can express this in the form of an odd integer, which is 2k plus 1. Now, if I do that, so if I have, so we could write since A and B are odd integers, then I can have 2 odd integers. I can have A is equal to 2m plus 1, another one B is equal to 2n plus 1. And that would require me to substitute both of these now into this expression here, and then break it down, simplify it as much as possible, factorize it, and show that this can never be in the form of an integer where it is divisible or is not divisible by 4. Either it is or it is not, right? Now, that's one way. Now, the question did not say to prove, right? It said to determine. So let's try and approach this in a little bit of an easier manner, right? For the sake of time and so on. So if m and n in this case are odd integers, then I can reduce this expression in terms of modulo 4, because it's said to determine for it being divisible by 4. Now, if it's divisible by 4, then I will have to check for odd integers. Either it's 1 or it is 3, right? For the modular. So for a modular method, if you want to put method, we could say that I'm going to let A and B be inside a set with 1 and 3, right? 1 and 3, mod 4. If at any point in time you're feeling a little bit confused, then you have to revisit the definitions of modular, right? Because the purpose of this is for the solutions, right? So for the theory of it, you'll have to revisit the lecture notes. So I know for any odd integer, so let's just say, so this is using that method from before, right? This line below is to use a little bit of a quicker way. So I know, so I should say we know for any odd integer, let's call it x, then I have that x squared is congruent to 1 mod 4. Therefore, in the question I have a cubed and b cubed. So x cubed will be congruent to, let's separate x cubed as x squared by x, will be congruent to 1 multiplied by x, which is congruent to x mod 4. Now, why am I doing this? I'm doing this to try and simplify a cubed plus b cubed plus ab in terms of modular arithmetic. So I can substitute the values 1 and 3, right, in pairs of odd integers to check and see if the value that I get after applying this definition here will give me something with a remainder of 0. If it does not, right, so if I do it for some of them and I get a remainder of 0, then that means that it's maybe true for some of them, right? If it's true for every single one, then it's true for all. So now I have to test it with different pairs. Now, of course, you could have taken the question itself with the a cubed plus b cubed plus ab and use random pairs of the odd integers 1 or 3, right? And see what values you get. Now, I'm doing this to simplify it for me. That way, where you substitute odd integer pairs 1 and 3 or 1 and 1, etc., into a cubed plus b cubed, etc., directly, that is fine as well. So just got some space, right? So so we have x is so this is congruent to x mod 4. So what does that mean for a cubed plus b cubed plus ab, which you could have used as well, which is completely fine. This will be congruent to a plus b now plus ab mod 4. Mod 4. So now I could use different pairs, right? So let's go case by case. Let's go case 1. Case 1, I can have where a is equal to 1 and b is equal to 1. So a is equal to 1 mod 4, and we could have b is equal to, is congruent, not equal to, sorry, congruent to 1 mod 4 as well. So let's directly substitute. So we'll get a plus b plus ab is congruent to 1 plus 1 plus 1 by 1, which is 1. So I'll get 3 mod 4. And this is not divisible by 4. So this case 1 does not work. So when a is 1 and b is 1, this does not work. So let's go again. Let's try case 2 now. Right, case 2. So it's already not valid here. Or rather, it's not valid. It's already false for, I want to use the wording of the question. It's already false for some odd integers, right? So what I'm going to check now from case 2 onwards is that, is it true for no integers at all? So case 2, so we could have when a is congruent to 1 mod 4. So I'm going to use 1 and 3 now. And b is congruent to, sorry, b is congruent to 3 mod 4. So then I will have a, so I remember that we're doing it like this, so I'm doing it like this, so I don't have to directly substitute numbers, because then I'll have 1 cubed plus 3 cubed plus 1 by 3 cubed. Actually, the statement is, sorry, 1 by 3, right? So I just don't want to have to cube anything. That's why I switched to this definition here, right? Where did I reach? Right. So a plus b plus ab, which will become 1 plus 3 plus 3 by 1, which will give me 7, which is congruent to 3 mod 4. And this is not divisible by 4 as well. So let's go again. Let's see now. Let's use something here. So let's go case 3 now. So I'm going to interchange 3 and 1. I'm going to put a as 3 and b as 1. So when a is congruent to 3 mod 4, and b is congruent to 1 mod 4. Then I have a plus b plus ab will be congruent to 3 plus 1 plus 3 by 1 again, which will give me 7, which is again congruent to 3 mod 4, which is not divisible again by 4. Let's go again. The last possible case will be where we have a is 3 and b is 3 as well. So I'll have a is congruent to 3 mod 4, and b is congruent to 3 mod 4. So I'll have a plus b plus ab will be equal to 3 plus 3 plus 3 by 3. So that's 9 and 6, that's 15. That's also congruent to 3 mod 4, which is not divisible by 4. So in every possible case, it is never divisible by 4. So we could say that the statement is true for no integers at all. So the statement, the statement is true for no integers at all. None of them works, right? None of them works. And this is using the definition of the modular arithmetic. Or you could have used this here and directly substituted into this, but you would have to cube each one and then add a multiplied by b and then factorize and then show that this could never be divisible by 4, which is quite long. So I'm just trying to do it the fastest possible way. Of course, you could have done this even faster by directly substituting 1 and 3 into this here, and then taking those values and determine whether those values are divisible by 4 or not, right? Which would have yielded the same result as this. Okay, so it's true for no integers at all. So moving on to part B now. Part B asks us to prove by contraposition that for all integers, n squared plus 2n is odd, right? Then n is odd. So it means that so question 2 part B says that so this one is actually a proof, right? So it's proof by a contraposition. Okay, so what is the original statement? The original statement is, if I want to ensure that we get the contrapositive correctly, right? So if n squared plus 2n is odd, then n is odd. So the contrapositive of this statement will be taking this part here and putting it in front, negating it, and similarly for this here. So the contrapositive is if n is even, then n squared plus 2n is even, right? This is what we have to prove here now. So okay, so we can assume now to start. So it's an assumption. So we assume that n is even. If n is even, then there exists some integer k such that n is equal to 2 by k. Now we're going to substitute this into n squared plus 2n. So I will have that n squared plus 2n will be equal to 2 by k all squared plus 2 into 2 multiplied by k. So this will be equal to 4k squared plus 4 by k, which will be equal to 4 into k squared plus k. Now, since k is an integer, then its square is an integer, and the sum of integers are integers. So it follows that. So you would write that first, and then you would say then since k squared plus k is an integer, it follows that 4 into k squared plus k is even. Okay, therefore, of course, you could have factorized this out differently if you wanted, as 4 into m, and then put m to be equal to k squared plus k, which is great as well, actually. And then you would say that m is an integer as well, right? And actually, I would suggest that you do something like that. So after this step, then you would say hence n squared plus 2n is even. So what have we shown? We have shown that, so we have shown that if n is even, then n squared plus 2n is even as well. Therefore, by contraposition, by contraposition, for all integers, for all n that's an integer, if n squared plus 2n is odd, then n is odd. We must tie it back to the original statement. Therefore, the statement is true. Okay, and then you put your box here, right? Of course, since the contrapositive is true, then the original statement is true as well. So you could probably add that line somewhere here as well, right? So this is the end of question number 2. All right, so moving on to question number 3 now. Question number 3, we have 2 mathematical induction proofs to do. So the first one asks us to prove that this thing here is divisible by 3 for all n greater than or equal to 1, right? So let me get some space. So question 3 now. So we have a proof, right? So proof. I'm going to take the statement that is given in the question, and I'm going to call it something so I don't have to keep rewriting the statement over and over again, right? So I'm going to say let Pn be equal to 10 to the power of n plus 2 plus 10 to the power of n plus 1. Okay? Of course, well, that was given in the question, right? So for n greater than or equal to 1. So I'm going to do the base case first, okay? So the base case, that is when n is equal to 1. So therefore, P of 1 will be equal to 10 to the power of 1 plus 1 plus 10 to the power of 1 plus 1, which will be equal to 10 to the power of 2 plus 10 1, that's 11. So we get 1 0 1 1. Okay, and since and since 1 0 1 1 is equal to 3 multiplied by, so divide this by 3, so 3 is 9, so you'll get 337. Then it follows that 1011 is divisible by 3. Okay, so the base case is true. So we have to say hence the base case holds. You want to write holds true. It holds true, and P of 1 is true. Okay, so that takes care of the base case. Now we have to get to the inductive part. So first we have to write our inductive hypothesis. So give something else. So the inductive hypothesis, of course I'm abbreviating here, but please don't. Right, so the inductive hypothesis is an assumption, so we must assume, right? We cannot say let, we must use the word assume. So assume that for some k greater than or equal to 1, P of k is true, right? P of k is true. We're going to make an assumption now. That is that 10 to the power, so I'm going to replace n with k now, right? 10 to the power of k plus 2 plus 10 to the power of k plus 1 is divisible by 3. Oh, you could have just write pk. Anyways, we'll do it like this. So that means I am assuming that, so I'm going to assume that there exists some integer. Remember, whenever we have our inductive hypothesis, at some point in time in the inductive step, I have to use this back again, right? I have to ensure that I use it. So I'm going to call this statement here 10 to the power of k plus 2, etc. something. So I'm going to say that, assume that there exists some integer. I'm going to use m, right? But you could use whatever you want. Some integer m such that 10 to the power of k plus 2 plus 10 to the power of k plus 1 is equal to 3 by m for some integer m. Okay, so this is the inductive hypothesis. So now we have to do the inductive step. Okay, let's see. Okay, so now we have the inductive step. Okay, this is where it gets a little bit tricky. So we want to show that pk plus 1 is true. So we must write that we want to show that pk plus 1 is true. That is we must show that, or we want to show that 10 to the power of k plus 1, 10 to the power of k plus 1 plus 2 plus 10 to the power of k plus 1 plus 1 is divisible by 3. So let me simplify this now and then start to work on the inductive step. Okay, so this means that now I am starting with 10 to the power of k plus 1 plus 2, that's 10 to the power of k plus 3 plus 10 to the power of k plus 1 plus 1. Okay, now we have a little bit of a choice here. Now the factorization here and the way that we expand this in order to use back the inductive hypothesis has to be done very carefully. right? So it means that we have different ways that we can approach this, right? So the first thing I'm seeing that I can do here, I can split this 10 to the power of k plus 3 as 10 to the power. So actually, let me write this on the side here. This is like 10 to the power of k plus 1 plus 2, right? And 10 is raised to the power of everything here. So the 10 to the power of k plus 2 could be one term, and the 10 to the power of 1 could be another term. So when the bases are the same, you can add the exponent. So that's the rule that I'm using here, right? So I'm going to split this as 10 by 10 to the power of k plus 2, right? I don't need to write to the power of 1, right? That's understood. Plus, same thing here. I'm going to split this as 10 to the power of 1, which is just 10, by 10 to the power of k, and then don't forget your plus 1. So I'm seeing I have 10 to the power of k plus 2, which I do have in the inductive hypothesis here, and I'm seeing that I have 10 to the power of k. Now, but I don't have the plus 1 here, right? So what we could do here, we have different things. We could add and subtract 9 or 10, right, throughout by factorizing. So I could factorize here the 10 out, and I could add and subtract 10. Or I could leave this as it is and add and subtract 9 instead, right? So I'm going to do the 9 first because I think it's a little bit easier to follow. So what I'm doing is I'm taking this number 10 here. Oops. I'm taking this number 10 here. I'm going to rewrite it as 9 plus 1 by 10 to the power of k plus 2 plus, again, 9 plus 1, 10 to the power of k multiply plus 1. Now, what I'm going to do is I'm going to expand the brackets. I'm going to take this number 9 and multiply it by this number 1 by this, and similarly here. Okay? So I'm going to get 9 multiplied by 10 to the power of k plus 2, plus 10 to the power of k plus 2, plus, now this time here now, we have 9 by 10 to the power of k, and then 1 by this, which will just be 10 to the power of k plus 1. Okay, where this here is this part here, and this here is this part here, right? And the plus 1 is the plus 1. We didn't touch that. Now, now I have all the terms from the inductive hypothesis. I have, let's count it. I have 10 to the power of k plus 2. I have 10 to the power of k by itself, and I have my plus 1. So I'm seeing the inductive hypothesis is here. So let me factorize everything and group those terms together now. So I'm going to get 10 to the power of k plus 2 plus 10 to the power of k plus 1 plus, and then all the other terms like this one here and this one here, I'm going to just shove it down to the end, right? Plus 9 by 10 to the power of k. Now I'm going to substitute. So let's write substitute the inductive hypothesis. Please don't write IH, just write it out properly. Okay. So we have, what did I use? 3 by something m. Okay, so I'm going to use 3 by m plus 9 by 10 to the power of k plus 2 plus 9 by 10 to the power of k. All right. Now notice that all of these here have some number that is divisible by 3 in it, which is good because I have to show that this thing is divisible by 3. So I'm going to factorize out now. Factorize out the number 3. I'll get m plus 3 by 10 to the power of k plus 2 plus 9, sorry, not 9, 3 by 10 to the power of k. Now, at this point in time, most students will just make a substitution, which is fine for all of this, and call it something and talk about the fact that these are integers, which we are supposed to do. But before that, we have a very important part that we must state, right? We have to say since k and m is greater than or equal to 1, because remember, we are inside the inductive step here. We have used the fact that n is greater than or equal to 1 in the question itself and applied that concept into the inductive step. So whatever is my new variable now, which in this case is m and k, this must also be greater than or equal to 1. That is my justification, right? So then m plus 3 by 10 to the power of k plus 2 plus 3 by 10 to the power of k is an integer. So instead of saying the m is an integer and the sum of integers are integers, we have this nice statement here from the question itself, which we could use instead of writing that, right? Is an integer. Let's call it something. Say, what do I use here? n, right? Say n. Therefore, we are saying that pk plus 1 is equal to 3 by n, right? And then n is an integer, right? And then we have the number 3. So once we multiply this, right, integer by integer, and it will be divisible by 3 because of this 3 in front here, right? So we have to say now, since p of 1 is true and the truth, of course, in any other words that you want here, right? I'm just writing this, but the information must be communicated, right, in any way that you want. Since p of 1 is true and the truth of p of, what did I have, k, implies the truth of pk plus 1, then by the principle of mathematical induction, p of n is divisible by 3 for all n that's greater than or equal to 1. Okay, so this is the best way, I would say, right? It's an objective statement to approach this. Now, if you know that you are not comfortable or you are not strong enough to be able to do a manipulation like this here or see it, what you could have done instead, now it just so happens in this question, because of the type of question and the way that the integers are arranged, right, and the type of factorization that is done as well, you could have taken the inductive hypothesis, rearranged it, and then put it back inside this step here. Okay, actually, let me write that out. Let me show you what I mean. What I mean is, take this here, right? Take 10 by 10 to the power of k plus 2, and first, actually, you'll have to factorize first. So let me write it out. So if you wanted, right, so you could probably write this if you want. You could have take 10 and factorize it out by 10 to the power of k plus 2, right, 10 to the power of k plus 1. And then remember that the inductive hypothesis here was all of this was equal to 3m. So what I would do is, because I don't have the number 1 here in this factorization, I don't have the number 1 inside here, but I want to use the inductive hypothesis. I would say from the inductive hypothesis, I would take 10 to the power of k plus 2 plus 10 to the power of k plus 1, which is equal to 3m, and just transpose it and make 10 to the power of k plus 2 plus 10 to the power of k is equal to 3m minus 1, right? And then substitute 3m minus 1 inside here. So I would get a 10 by 10 to the power of k plus 2 plus 10 to the power of k plus 1 would be equal to 10 to the power, 10 into 3m minus 1 plus 1. And then I would expand the brackets out and I would get 30m minus 10 plus 1. I would get 30 into 30m minus 9 and then I would get 3 into 10m minus 3, right? And the same logic applies. This is an integer, and the difference between two integers is an integer. You could call this n as well, and then 3 by n, and the same logic applies. Now, that's if you are not strong in doing a manipulation like this, but a manipulation like this will always be the safe way because it will always work out. It just so happens in this question we could have done this. It doesn't work out like this all the time, right? So this is part A. All right, so finally we're moving on to the last question now, the last part, sorry, of the last question, which asks us to, so first of all, they give us a sequence, and they say that AK is equal to this. And we have to use induction to prove this. So this is what we need to prove, right? This AN part here, not the AK part. We have to use that. A0 and A1 here are both of our base cases. This is strong induction, so we have more than one base case. Okay, so get some space. So this is 3 part B. Okay, so it will look similar to what we did before. We have an extra base case, and we need to do a little bit of work on the inductive hypothesis that is different. So of course, again, it's a proof. Now the part with AN, so let's just go back to the question very quickly. So this here, this is what we're going to prove. So if this is what we need to prove, then this here is I'm going to call it my claim, right? My claim is that AN is equal to 7 by 4 to the power of n minus 3 by 2 to the power of n. For every integer, we must write this for every integer n greater than or equal to 0. This is my claim. At the end, I have to show this somehow. So we could get started on the base case. So let's just get this out of the way. So the base case, right? So don't call it PN or anything like that from before, right? We have AN and we have something with AK. So we have to interchange between them. So we have to leave it as it is. So when n is equal to 0, I'm going to put 0 into all of this, right? And then I'm supposed to get what I was given in the question, right? So A0 would be equal to 7 by 4 to the power of 0 minus 3 by 2 to the power of 0, which is equal to 7 by 1 minus 3 by 1, which will give me 4. Now let's go back to the question. Is A0 4? A0 is 4. So this is fine. Now I have to do A1. We have to ensure both base cases first. So when n is equal to 1, I have A1 now being equal to 7 by 4 to the power of 1 minus 3 by 2 to the power of 1. I have 7 by 4 minus 3 by 2. So 28 minus 6, which is equal to 22. Let's check and see again. So yeah, so this is 22. So this is fine. So the base case holds. So we have to say now the base cases are verified. Okay, so now we can move on to the inductive hypothesis part. So for the inductive, remember again, it's an assumption, but we have to create a bound, right? A range, a specified range for our values. So assume again that for some integer a greater than or equal to 1, that the formula from before, right? That the formula holds for all integers. Now the integer you're going to choose has to be between 0, because my base case started with 0, and k. So I'm just going to use I, right? So integers I. So I'm gonna use I here. You could use anything that you want, J, L, doesn't matter, right? Once it's not key. With 0, so I is greater than or equal to 0, but less than or equal to key. So what are we assuming here? So that is, we assume that AI is equal to, I know you're accustomed with 7, sorry, with pk, and then wherever we see n we have to put k, right? We're going to do that, but we have to create a bound for us first, because this is a sequence, right? Oh, it's 4, sorry. 4 to the power of I minus 3 by 2 to the power of I. So we are saying that this formula here, this here, holds for some of this. So what this means in words is that we could say in particular, all of this is the inductive hypothesis still, right? In particular, it, meaning the formula, holds for when I now is equal to k, which you're accustomed to, and as well as I being equal to k minus 1. Because remember, when we do the inductive hypothesis, right, we have to make sure and use that in the inductive step. Usually it's either one more value or one less value. But in this case here, I'm using for one less value for the sequence, right? So in particular, again, if you want to use that, in particular, we may use AK, which you're accustomed to, 7 by 4 to the power of k minus 3 by 2 to the power of k. All right. And we also have to do for k minus 1 and as well a k minus 1, which is 7 by 4 to the power of k minus 1 minus 3 by 2 to the power of k minus 1. So all of this now is the inductive hypothesis. Now for the inductive step. So I have to use back all of this. So this is the inductive now step. So we must show, so we must write, we must show that the formula, again, the formula from before, which we spoke about, that the formula holds for n is equal to k plus 1. That is, in plain language, that is, we must prove that a k plus 1 is equal to 7 by 4 to the power of k plus 1 minus 3 by 2 to the power of k plus 1. Now, from the question, let's go back to the question again. I have AK. AK is equal to 6AK minus 1 minus 8AK minus 2. So that's why I said we have to use this, right? So using the recurrence relation, we have AK is equal to 6 into AK minus 1 minus 8 into AK minus 2. And we can write the fact that AK plus 1 now, plus 1, is equal to 6 into AK minus 8 into AK minus 1. So what I'm going to do now is I'm going to take the inductive hypothesis, because look, it's here. Look, I have AK and AK minus 1. So I'm going to put that inside here. Okay, so I'm going to substitute now. We're going to put and substitute the inductive hypothesis. Right? I just use IH. Please don't use it in the exam. So AK plus 1 is equal to 6, 7 by 4 to the power of k minus 3 by 2 to the power of k This is 4 to the power of k minus 1 minus 3 by 2 to the power of k minus 1. So now let's expand. Let's just expand these brackets. So I'll have 7 by, that's 42, multiply by 4 to the power of k minus 6 by 3, that's 18 by 2 to the power of k minus if that's 56 by 4 to the power of k minus 1 plus, because negative and negative, 8 24 by 2 to the power of k minus 1. Okay, so we have a couple ways that we could approach expanding this. First, separating all the indices and then breaking it down in order to get back where is it, this here, right? This 7, this here, let me just put this in green. This here, remember, this is a goal. This is what we want. When we put n is equal to k plus 1, this is a goal. This is what we want to get. So we want to break this down, and somehow at the end of it, we have to get this. So there are a couple ways that we could do this. We're going to do the easy way first. So I'm going to take these here, these indices that have negatives in them. I'm going to just break them down first. So as your side working, if you want to put like 4, so this is like side stuff, right? K minus 1 is the same thing as 4 to the power of k by 4 to the power negative 1. But anything with a negative exponent comes on the denominator side. So we have 4. Similarly for 2. Okay, so I'm going to take this now. So this is just side working, right? And put it back inside here to break it down. So I'll have continue with ak plus 1, right? It's still 42 by 4 to the power of k minus 18 by 2 to the power of k minus 56 multiplied by, this is 4 to the power of k now upon 4 plus 24 by 2 to the power of k upon 2. So now I'm going to cancel now and simplify this 4 with this 56 and this 2 with this 24. So I'll get 42 by 4 to the power of k. So all of this remains the same by 4 to the power of k. This is 12 by 2 to the power of k. Now I'm going to take everything that have the common terms in them, like this one and this one. I'm going to factorize them out. Okay, so I'll have 42 minus 14, that's 4 to the power of k, plus negative 18 plus 12 by 2 to the power of k. So let's simplify some more. So I'll have 28 by 4 to the power of k minus 6 by 2 to the power of k. Now we have to break this down, 28 and the negative 6, in terms of integers. But remember, I want to make it match these here. So once the bases are the same, I can add the indices, right? So I know 7 by 4, that's 28. So I'll put 7 by 4 multiply by 4 to the power of k minus 3 by 2 is 6. So we have 3 by 2 by 2 to the power of k. So this will be 7. So the bases here are the same. So I can add the indices similarly here as well. So we have 4 to the power of k plus 1 minus 3 by 2 to the power of k plus 1. Now, take this and look at it and see if it matches this form here. Is it the same thing? It's exactly the same thing. So this is what we wanted, right? So we could say, and this is exactly the formula for n is equal to k plus 1. Okay? And then we could end off all of this now by giving a other statement, just like we did for the last part. Okay? So we could say we have shown that if, right, because remember the inductive part was the hypothesis part, was an assumption. So we have to use the word if here. So we are shown that if the formula holds for all values, because remember we created a new bound for our values, all values up to k, because remember I said up to k, right? Not after k, because of this here, right? Remember it was greater, I was greater than equal to 0 but less than or equal to k, so up to k. So we stopped at the k value. Values up to k, then it means it must also hold for k plus 1. Of course, then you end up by saying by the principle of mathematical, just include here strong induction. It's supposed to say strong induction. The formula, which was an 7 by 4 to the power of n minus 3 by 2 to the power of n, is the true, right? It is true and it is valid for any integer n greater than or equal to 0, right? And you end off the proof there. Now I said that there was a different way you could have done this factorization. So I'm just going to talk about it briefly. Some students may prefer that. So at this stage here in the factorization, if you could not have seen to do something like this and break this down, what you could have done instead, you could have said that, so from this step here, from this arrow here, right, you could have broken down the first term, meaning this term here, and the third term, meaning this term here, in terms of powers of k minus 1, right? And the second term in terms of powers of k minus 2, and so on. Meaning that I could have taken those terms and write it like this. So I'm going to use a different color so you can see it. So I would have taken the first term and the third term. So I'll take 42 by 4 to the power of k and rewrite it as 42 by 4 by 4 to the power of k minus 1, right? So it's like I'm working backwards here, right, to get back to this, right? You could have done it like this as well. So this would give us 168 by 4 to the power of k minus 1. Similarly, for 18 by 2 to the power of k, work backwards. So you'll get something like this. So same k minus 1. So you'll get 36 by 2 to the power of k minus 1. Because when I subtract, when I add the indices here, I'll get back k. That's the point of this negative, this negative 1 here, right? And then I would have taken this now and rewritten it inside my new ak, which would have been ak plus 1. This is 168. 168 by 4 to the power of k minus 1 plus 24 by 2 to the power of k minus 1. So now I have all the powers in terms of k minus 1. So it would have been easier for me to factorize if you want to do it like this. So in this case, I would have collected the like terms as follows, right? 168 and 56. So I'll have 168 minus 56. Is that correct? Yeah. 4 to the power of k minus 1 plus, put the negative 36 in front, right? If you want. And then put this here. 2 to the power of k minus 1. So that means I would have gotten 168 minus 56. That is at 112. Yeah, 4 to the power of k minus 1. Negative 36 plus 24 has negative 12 by 2 to the power of k minus 1. Okay. Then you could factor these coefficients here. So the 112 by 4 to the power of k minus 1 would become, so I get something here. I wouldn't get something that is in immediately into 4. to get my 4 to the power of k plus 1. So I'll have to try something like 7 by 16. This is correct. 7, 32, correct. Yeah, this is correct. By 4 to the power of k minus 1. And then for the 12, do the same thing. Oh, sorry. For the 12, do the same thing. So I have negative, so minus 4 3s are 12. Does that work? 3 by 4 to the power, yeah, 2 to the power of k minus 1. And then I'll separate this 4 as 2 squared, right? And then 2 minus 1 for this 1 here will come out. I'll just have 2 to the power of k plus 1. So I'll have 7 by 4 to the power of k plus 1, because 16 is 4 squared. 4 4 is 16. So the 2 that will come here, okay, let me write it. This will be 4 squared, right? And then the bases are the same. So 2 minus 1, that's how I'll get the plus 1 here, right? And then do the same thing for this. So I'll get minus 3 by 2 to the power of k plus 1. So you see the answers are exactly the same. Both of them will give you the same required formula, right? So this is the end of coursework exam solutions for exam 2.